In a double replacement reaction, you will have two ionic compounds, and they'll switch partners, positive and negative, to give you two new ionic compounds. These reactions are not redox reactions because all of the ions will retain their original charges, so there's no transfer of electrons. Let's look at how to predict these products. We will predict these products. So it's a good idea to start by figuring out the charges on everything, and you can use your periodic table and your memorized polyatomic ion charges to do this. Let's see. Okay, so potassium has a +1 charge, chlorine a -1. Lead is not in a column on the periodic table that we can tell, but nitrate, NO3, has a -1 charge. So I could figure out from this 2 that this lead must be a +2. Remember that these numbers are normally crossed down there. And so by kind of crossing up, we can figure out what the charge is on that lead. Another way to say that is that we know that this whole side, its charge would be -2, and so we know that this must be +2 to balance with that. Anyway, so figure out the charges because they'll remain the same when you go to the other side. So let's figure out our first product. And so I'm going to start with potassium. Potassium will always be in front because it's the positive ion. In a formula, the positive ion is always first. And now what will go with potassium? The other negative ion will. So basically what I'm doing, I'm putting the front part of one compound with the back part of the other. So I'm going to put nitrate here. Its charge is -1. And then I need to look at this and make sure this is a good formula. In other words, cross down these numbers. And if I cross down these, I would just have a 1 and a 1. So that doesn't do anything. We don't need to show 1s. So that is the good formula for potassium nitrate. The other product is going to involve lead. And lead will still have that +2 charge. And then lead is going to be with the chlorine with its -1 charge. And then on this one, I do need to cross down those numbers, the charges, to get that I have a 1 there, and we don't have to show 1s, but we need a 2 out there. Okay, so that is the correct formula for the lead 2 chloride, lead chloride. Okay, so we've got good formulas. Now, I need to clarify something a little bit. Why did we keep this 3 here? Why didn't we just put NO? And the reason that we did is that we keep this because it's part of the polyatomic ion. But this 2 we don't keep. And it's because that 2 came from this charge. That 2 is there because the lead had a +2 charge. Okay, so we'll be watching that. Let's go ahead and balance this. If we look at, on these, you can just look for something that's not balanced. And the polyatomic ions stay together, they don't break apart, and like we kept that 3 there. So we can say there are 2 nitrates here, and we can treat it just like an element when we balance. There are 2 nitrates, and there's only 1 nitrate here. So I'll put a 2 in front there. And that just affected the potassium, so I'll go to potassium next. There are 2 potassiums in my product, so I'll go to my reactant. I only see 1, so I'll put a 2 in front there. Now there are 2 potassiums and 2 potassiums. There are now also 2 chlorines and 2 chlorines. So chlorine is balanced, and then we'll check lead. There's 1 lead and 1 lead, so that one is completely balanced. Let's try this next one. And on this one, I need to tell you a few polyatomic ions you may not know. the font is kind of bad here because that's a capital I. Iodate is a polyatomic ion. It's not one I have my students memorize, so I'll point it out to you here. This one is carbonate. That will help us in writing these formulas correctly. Okay, so let's put our charges up here. Sodium's in the +1 column. Iodate, I just told you, is -1. Potassium's in the +1 column, and carbonate is in the -2 column. So when we start figuring out our products, we're going to put the positive part of one with the negative part of the other. So I'll start with the sodium is going to go with the carbonate. Think about the charges that are on each of these. We're crossing those charges down, so we need a 2 right there. And this would bring a 1 out here, but we don't need to show a 1. Notice we kept the 3 because it's part of the polyatomic ion. Okay, so that's a good formula for our sodium carbonate. Let's go to our other product. Our other product involves potassium and iodate. Potassium's in the +1 column. Iodate has a -1 charge, as I told you. So if we cross these charges down, it does nothing. That's a good formula for potassium iodate. Now let's balance. Spot something that's not balanced, and what stands out to me is the sodium's not balanced, so let's just start with sodium. There's 2 sodiums in the product and only 1 in the reactant. So I'll put a 2 here. And then what should I balance next? I should balance iodate next because this 2 just affected iodate. So there's 2 iodates here. In the product there's only 1 iodate, so I'm going to put a 2 there. That just affected potassium. So there's 2 potassiums in the product, 2 potassiums in the reactant. Last, I'll check carbonate. There's 1 carbonate ion in the reactants and only 1 in the product. So that one is balanced. Okay, and just another reminder, why didn't we keep this 2 here when we brought it over here? This 2 came from the charge, so you don't keep it when you project the product. Why did I keep this 3 here when I brought it over to the product? Because this 3 came from the polyatomic ion carbonate. The polyatomic ions remain intact, so that's why we kept that 3. Okay, let's look at another reaction. Neutralization reactions are a type of double replacement reaction. And like all double replacement reactions, the charges remain the same as you go across, so they are not redox. Charges don't change. Let's see. So let's put some charges up here. Now technically HCl, that's 2 nonmetals, you would say that it's not ionic. You would think it was covalent. But acids act ionic, and when you put them in water they in fact do become ionic. So we'll treat that as though it's ionic. Magnesium's in the 2nd column of the periodic table. This is OH is hydroxide. It has a -1 charge. So when we bring our products over, this time instead of starting with the hydrogen one, I'm going to start with the magnesium compound. What ion is with magnesium? So I have the front part of this one, and I'll put the back part of the other reactant. So I need chlorine. And then my charges on this, the magnesium is +2 and the chlorine is -1. So if I cross those down, I need a 2 right there. My other product, I take the front part of this one and the back part of that one. So it's HOH. And we're going to treat this as though it's ionic. So we'll have a hydrogen ion with a +1 and a hydroxide ion with a -1. Now that might look funny. That is written as though it's hydrogen hydroxide. But we know that really it's water, and it's not an ionic compound at all. but it will make balancing this easier to write it HOH. And you know, this is not just something silly that I do. A lot of chemists will write HOH for water in different circumstances. So let's start our balancing. What's not balanced? Well, chlorine's not balanced. Let's start with it. There's 2 chlorines here in the product and only one of my reactants. So I'll put a 2 in front here. And that just affected this hydrogen ion. So remember, this time I'm not counting hydrogen atoms. I'm treating hydrogen ions and hydroxide ions as though they're different. So there's 2 hydrogen ions, and here there's only 1 hydrogen ion, this in front. So I'll put a 2 there. That gives me 2 hydroxide ions as well. So I go to my reactants, that's 2 hydroxide ions. There's 1 magnesium, 2 chlorines, and we're back to the beginning. And so that is balanced. One more thing I'll point out. Acid plus base yields salt and water. That is our general reaction for a neutralization.